Good morning. I thank Francisco Ubero and Irene Palacio and the organizing committee of the conference for inviting me here. As I had written to Francisco and Irene last December, I was quite surprised by this invitation because I don't consider myself to be an expert on thin films. But they assured me that their invitation was not emailed to me by mistake. So here I am, and here all of you are. I will follow the advice given by the king to the white rabbit in the book Alice in Wonderland. Begin at the beginning, he said. I have been interested in curves from as far back as I can remember. This may have been the result of watching regularly, as a child, snake charmers. The cobras describe time-varying curves. Curves in space have a property called handedness, which you can appreciate by contrasting a right-handed seashell with a left-handed seashell. Both shells in these pictures come from the same species, the Florida lightning whelk, but one is left-handed, the other is right-handed. Curves and chirality or handedness underlie most of my research during the last 40 years. Light can have chirality too. In air, it can be either right circularly polarized or it can be left circularly polarized. In air, light of either chirality moves with the same speed, and the attenuation rate for both chiralities is minuscule. But neither assertion is true in many organic substances, and the polarization state of light gets distorted upon passage of light through a slab of such a substance. Solutions of 3 sugars are commonly used to demonstrate the visible effects of chirality. Glucose, also called dextrose, has right-handed molecules. Fructose, also called levulose, has left-handed molecules. The sucrose molecule is a combination of a glucose molecule and a fructose molecule minus a hydrogen atom. Sucrose molecule is also right-handed.
This is a solution of sucrose. It's a chiral molecule and it's dextrorotatory, i.e. it rotates plane polarized light to the right, so it's now able to pass through the second filter. Other sugars, like glucose and fructose, are chiral too. Glucose rotates light to the right, hence also been known as dextrose. Fructose, which is sold in supermarkets as fruit sugar, rotates light strongly to the left, and is also lesser known as levulose. But have I just added a glucose solution or a fructose solution? Both look the same. However, if you turn one of the filters back and forth, you can see our solutions are rotating in opposite directions. The one on your left is fructose.
Sugars are examples of microscopic chirality. The linear dimensions of their molecules are minute fractions of the wavelength of light that we can see. A random dispersion of miniature metallic springs is also, in effect, an isotropic chiral material, but at microwave frequencies. The sample that you see was fabricated by my colleague Alvaro Gomez of Universidad de Cantabria for operation in the gigahertz range. In some materials, chirality can be more pronounced for electromagnetic waves propagating in one specific direction than in other directions. Such materials are called Faraday chiral materials. There can be non-homogeneous variants of these materials as well. In the descriptors of all of these materials, a mathematical operation called the curl appears. The curl is a rotational operation. Rotations can be left-handed about a fixed axis, or rotations can be right-handed about a fixed axis, as this ballerina will show you. The effects of isotropic chirality are used in sugar industry, pharmaceutical industry, and for analytical chemistry. Nevertheless, isotropic chirality has weak effects. What is needed for stronger effects is a curl enhancer, probably made by a hair care company. In 1992, I came across a mineral called ulexite. It is opaque, except when you view through it along a specific direction. Then it is quite transparent. A scanning electron micrograph shows the structure of ulexite. It is like a mass of parallel and straight glassy fibers all stuck together. One can see along the lengths of the fibers, but not in directions that are transverse to the fiber lengths. I called my colleague Russ Messier. You would know him well. He was one of the pioneers of morphological studies in thin films. I asked Russ if similar substances can be made in a lab. He said, "Of course." And with that answer, a whole new world opened up for me. Russ explained to me the industrial process of physical vapor deposition, which has been around now for over 160 years. You all know it very well, but let me introduce it anyway here. Put a source material in a chamber and evacuate that chamber. The source material shall evaporate. Collect the evaporant flux on a substrate. A thin film is formed on a substrate. If the conditions are right, nominally parallel columns or nanowires grow. This assembly is called a columnar thin film. Here is a scanning electron microscope image of a columnar thin film made of zinc selenide. So I asked Russ, could we rotate the substrate during deposition? Again, he said, yes, of course. Well, I said, rotate the substrate about a central normal axis passing through it, and nanohelices will grow instead of nanocolumns. This is what you see in this scanning electron microscope image from 2018. This film is also made of zinc selenide. Note the structural periodicity in the thickness direction, which is of course in the vertical direction here. Also, I said to Russ, if we rotate the substrate about a tangential axis, then nano zigzags will grow instead of nano columns. This is what you see in the scanning electron microscope image of a zinc selenide film from 2017. This film is also structurally periodic in the thickness direction, which is vertical here. Finally, it should be possible for both kinds of rotations to take place simultaneously, and then quite complex nanomorphologies will emerge. And that is what you see in the films labeled B to E. These films were made in 2013. Structural periodicity is maintained in these films too, in the thickness direction. These scanning electron microscope images are of films made in this century. Back in 1994, after I had explained the concept to Russ Messier, the issue arose as to how would that concept be implemented. Russ advised me to call Michael Brett at the University of Alberta. Our collaboration over the next 3 years resulted in several papers. Here I'm showing you the scanning electron microscope image of a chiral sculptured thin film, which of course comprises nanohelixes. This film was made in 1995. And that is how the area of sculptured thin films began. However, unbeknownst then to me, Young and Cowell had reported the fabrication of a chiral sculptured thin film in 1959. They had not obtained scanning electron microscope images. Such microscopes were not common enough then. But there is enough optical evidence in their short paper for their claim. That paper had become obscure, getting just 5 citations from 1960 to 1996. That's 37 years. In 2008, I set up a thermal evaporation system. In this video, you can see a platform that is rotating. If a theorist, that is me, could do it, clearly architected nanocolumnar morphology is not difficult to realize. The apparatus for making sculptured thin films is quite straightforward to design and assemble. Formally then, sculptured thin films are assemblies of parallel curved nanowires of specific shape. The shapes can be nematic, that is 2-dimensional, or they can be helicoidal, that is 3-dimensional, and one can make combinations of these. We can even change the shapes of nanowires abruptly during growth. In other words, sculptured thin films can be vertically sectioned, as you can see in this scanning electron microscope image. The change of shape can occur within 20 to 30 nanometers of growth, which is optically abrupt. This is because sculptured thin films comprise 1 to 3 nanometer clusters as building blocks. The intercolumnar as well as the intercluster porosities can be controlled by varying the deposition conditions. Many integrated optical devices become possible thereby. Let me talk about a few. In presenting these optical applications, I will concentrate on chiral sculpture thin films, which are, by now you realize very well, forests of parallel nanohelixes. These sculpture thin films can function in optics as circular polarization filters. If a chiral sculpture thin film is structurally right-handed, it preferentially reflects right circularly polarized light incident on it in a wavelength range called the circular Bragg regime. This regime is identified as the dark blue band in the spectrum of TR. The right-handed chiral STF does not reflect left circularly polarized light in the circular Bragg regime. And that is why in the spectrum of TL, you do not see a blue band. So, a chiral sculpture thin film functions as a band stop filter for right circularly polarized light. If a chiral sculpture thin film is structurally left-handed, it preferentially reflects left circularly polarized light in the circular Bragg regime, but not incident right circularly polarized light. And therefore, in the spectrums here, there is no blue band in the spectrum of TR, whereas you can see a prominent blue band in the spectrum of TL. So, a structurally left-handed chiral sculpture thin film functions as a band stop filter for left circularly polarized light. Suppose we cascade a structurally left-handed chiral sculpture thin film and a structurally right-handed chiral sculpture thin film. Both are otherwise identical. Then we get a band stop filter for all polarization states. And that is why you can see the blue band here in the spectrum of TR as well as in the spectrum of TL. And if both handednesses are intertwined period by period, again we have an all polarization band stop filter, and you can make out in the spectrums here the dark blue bands that is there for both TR and TL. If we wish to shift the circular Bragg regime after deposition, one way could be to anneal the chiral sculpture thin film. Annealing alters the morphology. Here are scanning electron microscope images of a titanium dioxide chiral sculpture thin film. Before and after annealing, the morphology definitely has changed due to annealing. The effect of annealing is a blue shift of the circular Bragg regime. The black curve indicates the circular Bragg regime before annealing, the red curve after annealing. The red curve is blue shifted with respect to the black curve. Multiband circular polarization filters can be made by growing a stack of different chiral sculpture thin films. Chung Kwan Hwangbo in South Korea grew a stack of 3. As predicted by theory, there were 3 circular Bragg regimes. Thus, one can envision many sectioned sculpture thin films as entire optical systems. Another example, you can see a 90-degree central twist defect in a chiral sculpture thin film incorporated during fabrication. This was done deliberately. The substrate was rotating at a normal speed. All of a sudden, it was rotated by 90 degrees very rapidly. Thereafter, rotation at the normal speed was resumed. The effect of the 90-degree twist defect is a transmission spike in the spectrum. This transmission spike indicates a reflection hole. The circular Bragg regime is generally 50 to 100 nanometers wide. This spectral hole is around 10 nanometers wide. Post-deposition, the spectral hole filter can be tuned, for example, by dipping in a weakly acidic solution. Chemical etching leads to progressive columnar thinning, which causes a progressive blue shift. Here you can see the transmission spike at 0 minutes, then at 10 minutes, then at 20 minutes, 30 minutes, 40 minutes, and 80 minutes of etching. The wavelength decreases. The spectral hole is a sharp feature in the spectrum. Sculptured thin films are porous. If the void regions of a chiral sculptured thin film with a twist discontinuity are infiltrated with the fluid, the spectral hole shifts. Thus, the device can be used as a fluid concentration sensor, as has been experimentally verified by Ian Hodgkinson. Controllable sources of circularly polarized light can be made. A chiral sculptured thin film was fabricated with a central layer defect. The defect comprises two spacer layers sandwiching a layer of quantum dots that were optically excited. Thereupon, visible circularly polarized light was emitted. Since the chiral sculptured thin films fabricated were left-handed, a spectral hole showed up in the reflectance spectrum for incident left circularly polarized light, when the quantum dots had not been excited. When the quantum dots were excited, the emission spectrum had a peak for left circularly polarized emission. In a different experiment, a columnar thin film serving as a quarter wave plate and a structurally right-handed chiral sculptured thin film were grown on top of one mirror of a vertical cavity surface emitting laser. The laser was pumped electrically. It emitted right circularly polarized light of 848 nanometer wavelength and line width of 1.06 nanometers. Next, suppose that a chiral sculptured thin film is grown on top of a metal film. The interface can guide more than one surface plasmon polariton wave with different characteristics at a specific frequency. This had been theoretically shown in 2008. It was experimentally confirmed the following year in the usual prism-coupled configuration of Kretschmann and Rather. In the angular spectrum shown, the two arrows point to the excitation of two different surface plasmon polariton waves at 633 nanometer wavelength. This phenomenon can be exploited for sensing. Here you can see angular shifts with sugar concentration in sweet water. Let me pause here to assure you that all experimental results I have presented so far have been validated against theoretical studies involving the solution of Maxwell equations. But I am not going to inflict equations on all of you. Please see this book if you are interested. Let me return to experimental results. In order to sense immunoglobulin G or IgG in water, a gold nanoparticle layer was deposited between two chiral sculptured thin films that are otherwise identical, and protein A was bound to the gold nanoparticles. Then aqueous solutions with different concentrations of IgG were put inside the chiral sculptured thin film, and the reflectance versus angle of incidence data was measured at 633 nanometers wavelength. These data were used to train a support vector machine. This system could then be used to predict IgG concentration in an unknown sample with at least 93% accuracy. About 2 years ago, with Manik Pradhan of Kolkata, I began researching the spin-dependent splitting of light in the photonic spin Hall effect induced by the Pancharatnam Berry phase. We used the quantum weak measurement technique. Although published, the results are too undigested for presentation in this talk, except that both the Pancharatnam Berry phase and the spin-dependent splitting of light were found to be affected significantly by the columnar morphology. Our investigations continue. Next, by depositing sculptured thin films on substrates that have been lithographically patterned, the nanoscale and the microscale can be blended together. As in these metallic sculptured thin films, you can see these have been made of chromium, molybdenum, and aluminum. And then we can do the same thing with dielectric sculptured thin films. These are made of silicon oxide. These structures could be useful for photonic bandgap engineering, labs in a chip, etc. One of my students is currently investigating these 3D photonic crystals. Here I show you a columnar thin film of silver deposited on a topographic substrate with parallel ridges. Asymmetric diffraction of light took place, leading to a simple method for fabricating blazed gratings. We have been able to coat even such complicated substrates as a butterfly wing and an entire fly in an aim to develop copycat technology. Let me use a child's toy called round pinpoint to illustrate my approach to bioreplication using sculptured thin film technology. On the left is a collection of parallel cylindrical pins standing upright over a plane surface. On the right is the same collection of pins over an undulating substrate. The tops of the pins reproduce collectively the substrate features. The smaller the cross-section of the pins, the better is the top surface reproduction of the substrate features. The aim now is to grow upright columns. We still use oblique angle deposition, but the substrate is made to rotate rapidly at about 1 revolution per second. Upright columns then grow. This is the key step in a bioreplication technology. We begin with a biotemplate, deposit on it a columnar thin film comprising upright columns of nickel, electroform to thicken the nickel columnar thin film for mechanical sturdiness, remove the biotemplate, and we now have a die or a mold for stamping or casting. Here is an array of corneas from blowfly eyes prepared for coating by a nickel columnar thin film. On the left is the scanning electron microscope image of a cornea. On the right is a scanning electron microscope image of its bioreplicated copy made of PVDF. Note how good is the replica. A real success of bioreplication came in the fight against the spread of infestation by emerald ash borers. This pest species from northeast China has been decimating ash trees of some 25 species in both the United States and Canada. My students used are bioreplication technology to make decoys labeled C2E of the insect A. These decoys of female emerald ash borers were used to lure male emerald ash borers for mating. Female emerald ash borers, as well as their bioreplicas, were stuck to adhesive sheets in order to lure male emerald ash borers flying overhead. Our bioreplicated decoys were 40% more successful than dead females in luring male emerald ash borers. We went on to construct an electrocution trap. See how it works. Yep. Again. Yep. Another extension was to develop latent finger marks. Finger marks on transparent glass are not always easy to see, but when a columnar thin film is deposited, the finger mark is developed. You can see the ridges and even the pores in the ridges. The scanning electron micrograph here shows the columnar thin film that grew on top of the finger mark residue. This method was successful even in exposing latent finger marks on cartridges after discharge, and also on compact discs, as well as polymer banknotes. Fingerprints often contain DNA. Here is a partial bloody finger mark that was developed by depositing the columnar thin film of a chalcogenide material. Subsequent DNA analysis showed almost perfect identification of the donor of the partial bloody finger mark. Single nucleotide polymorphism analysis has also been performed on environmentally insulted fingerprints that have been developed using columnar thin films, and the results have been deemed satisfactory by my forensic science colleagues. Now let me move on to the final topic, engineered multifunctionality. There are two ways to realize multifunctional systems. One way is to assemble together many single-function devices and systems. Excellent examples are the Swiss Army knife and the Xerox copier. The other way is to use specially designed composite materials. The second option is of interest to me, and I began to think about a general principle for multifunctional composite materials that may be called metamaterials, which are macroscopic composites designed to produce an optimized combination of two or more responses to specific excitation. The general principle of engineered multifunctionality, in my opinion, is to have lots of surfaces and interfaces in any fixed volume without compromising mechanical strength. That general principle led me to the concept of a MyMUM, microfibrous multifunctional metamaterial. Microfibers provide preferred pathways to transport charges, ions, atoms, molecules, thermal energy, mechanical stress, etc. They also give rise to porosity to store other materials as well as to facilitate volumetric changes. They make the overall material flexible, pliable, and resistant to cracks. With increased surface area per unit volume, some surface phenomenon may be promoted over volumetric phenomenon. For some years, I have been involved in making MyMUMs of parylene C. This is a polymer approved by the US Food and Drug Administration to coat implantable prostheses, pacemakers, and catheters. It is also used for packaging of electronic devices. Here you see a chiral mimium of parylene C. The length scale is not a few hundred nanometers, but a few tens of micrometers. Fabrication takes place using physicochemical vapor/angle deposition. There is a chemical component, otherwise it is the same as physical vapor deposition. Columnar mimiums of parylene C were investigated as interlayer dielectrics for flexible electronics. The atoms were directed at an angle chi sub v with respect to the substrate plane, but the microfibers were slanted at an angle chi with respect to the same plane. With increasing chi sub v, chi increases and porosity decreases. My group went on to investigate mechanical properties, conduction mechanisms, and electrical stability of the columnar mimiums of typical thickness 100 micrometers. The more porous, the softer the columnar mimiums. Both the Young's modulus and the yield strength can be as low as 2 orders of magnitude lower than of bulk parylene C. The dielectric constant can be as low as 2.2 at 1 MHz frequency, which is desirable for interlayer dielectrics. This value is about 30% of that of bulk parylene C. DC conduction is due to the Poole-Frankel mechanism rather than the Schottky mechanism. Small polaron tunneling is a dominant AC conduction mechanism. Analysis of the leakage current after the application of constant voltage stress indicates that the capacitance will degrade by 20% in 10 years. In other words, parylene C columnar mimiums may be very suitable as interlayer dielectrics. Moving on to biomedical applications, the cross-sectional scanning electron microscope images of 3 different parylene C mimiums are shown here. Note the microfibrous morphology and the periodicity for chevronic and chiral mimiums. Columnar mimiums are of course not periodic. Look at the top surfaces. 3 types of mimiums have similar top surface morphologies. Compared with a dense thin film, the surface of a mimium is much rougher. The top surfaces are therefore hydrophobic. Hydrophilicity is also possible through oxygen plasma treatment. These surfaces can be used for tissue culture. In an experiment, the best attachment of human fibroblast cells came for tilted columnar mimium when serum proteins were present, but oxygen plasma treatment was not needed. The attachment of specific proteins can also be fine-tuned. Mimiums of parylene C may be useful as cell culture substrates for pathology laboratories, as coatings for medical prostheses and surgical equipment, as biosensors, and for drug delivery. They can be volumetrically functionized as well, and they can be optically monitored. The same technology can produce mimiums for ultrasonics. Here, the chiral mimium has a period of about 20 micrometers. It can act as a band-stop filter for circularly polarized shear waves. Because of its 20 micrometer period, the same mimium will have terahertz applications as a band-stop filter for circularly polarized electromagnetic waves in the terahertz regime. So 2 functionalities can come out of exactly the same mimium, but that is not all. By impregnation with quantum dots, we can get these mimiums to emit visible and ultraviolet light. But that is not all either. These impregnated mimiums could function as luminescent concentrators for solar cells, absorbing ultraviolet light and converting into visible light for photovoltaics. I have a student currently working on this matter. Unimpregnated mimiums could function as light-trapping textured coatings for photovoltaic solar cells. We can grow cells on them and monitor their state by changes in fluorescence. Now I hope that I have provided you a vision of engineered multifunctionality possible through materials with architected columnar morphology. Before concluding, let me say that over the last 30 years, I have been immensely helped by colleagues at Penn State and throughout the world. And students, mostly at Penn State, but one from IIT Kanpur and one from IIT. That's all, folks.